A telescope just found something that should be impossible. James Webb pointed at a patch of sky the size of a grain of sand and found thousands of galaxies hiding in what we thought was completely empty darkness. Massive, structured galaxies already built just 300 million years after the Big Bang, when science told us the universe was still too young to build anything. Then came black holes that grew to monstrous sizes in no time at all, and a total galaxy count so staggering, scientists went from hundreds of billions to trillions overnight. Everything you were ever taught about the universe's size shattered in a single image. What Webb found at the edge of time will show you the true scale of the universe, and the number is so incomprehensibly vast, it will make the entire world around you feel like dust. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. The story of the universe, as we understood it, was one of the most beautiful things science had ever produced. Not beautiful because it was simple, it was anything but simple. Beautiful because it was coherent. Every piece fit against every other piece. The age of the universe, the structure of galaxies, the distribution of matter across billions of light years, all of it lined up, all of it confirmed again and again by every telescope we pointed at the sky. We had, as far as the world's best cosmologists were concerned, solved the basic outline of cosmic history. And then we built a telescope that suggested we might have been wrong. But before we get to that, we need to understand what we thought we knew. Because the model wasn't guesswork. It was the product of generations of careful observation, refined mathematics, and some of the most precise instruments ever constructed by human hands. The story begins 13.8 billion years ago. That number, 13. 0.8 billion years is the estimated age of the universe itself. To get a sense of what that means, if you sat down right now and counted every year of cosmic history at a rate of 1 count per second, without sleeping, without pausing, it would take you roughly 437 years to count to 13.8 billion, longer than the entire span from the founding of the first European settlements in the Americas to today. Every war, every invention, every century of human civilization since then, all of that just to reach the age of the universe in raw seconds, and that is merely how old it is. The story of what happened inside those 13.8 billion years is something else entirely. And at the very beginning of all that time, according to our best understanding, came the Big Bang. The Big Bang was not an explosion in space. That is one of the most common misunderstandings in all of science. It was an expansion of space itself, every point in the universe stretching outward from every other point simultaneously, like the surface of a balloon being inflated from the inside. In the first fraction of a second, the temperature was so extreme that matter and energy were essentially the same thing. Then, as the universe expanded and cooled, the first subatomic particles formed, then the first hydrogen and helium atoms, then silence. This is where the story enters what cosmologists call the Dark Ages. Not metaphorical darkness, literal darkness. For roughly 100 to 200 million years after the Big Bang, no stars existed anywhere in the universe. No light of any kind, just cold hydrogen gas, slowly drifting and clumping under the invisible pull of gravity, filling a universe that was utterly, completely, profoundly dark. Imagine an ocean with no surface, no bottom, no shore, just cold water in every direction, forever. No light from above, no heat from below, nothing. That is what the universe was for tens of millions of years, a vast, lightless sea of gas assembling itself in the dark. And then, gradually, something changed. The hydrogen grew dense enough in certain regions for gravity to take hold completely. Clouds of gas collapsed inward, heating as they compressed. until the pressure at their cores became so extreme that hydrogen atoms began to fuse together into helium, and light poured out for the first time. The first stars ignited. Scattered, isolated, enormous compared to stars today, but real. The universe had illuminated itself. What followed, according to the model, was slow, gradual, measured. Small clusters of stars drew together under gravity into early galaxies, dim, irregular, modest. Those galaxies collided and merged over millions of years to form larger ones. The larger galaxies gathered into groups, then clusters, then the vast interconnected web of structure that fills the observable universe today. Galaxy formation, in the model we had, was a patient process. The universe had to earn its complexity. It had to build up slowly from primitive beginnings. This was the accepted story, and it had a name. Scientists call it the Lambda CDM model. The name is a mouthful, but the idea is straightforward. Lambda refers to dark energy, a mysterious outward pressure woven into the fabric of space itself, driving the universe to expand faster over time. CDM stands for cold, dark matter, an invisible form of matter that cannot be seen or touched, but whose gravitational influence shapes the way galaxies and galaxy clusters form and move. Together, these two components, alongside ordinary matter, describe a universe that behaves in very specific, testable ways. And for decades, every test confirmed it. The clearest confirmation came in 1995, when NASA pointed the Hubble Space Telescope at a patch of sky so small it seemed almost absurd. The target was a region near the Big Dipper, a region that appeared to any ordinary telescope to be almost completely empty, just darkness. Scientists held the Hubble there for 10 consecutive days, collecting every photon of light it possibly could from that single sliver of sky. Picture this: take a grain of sand, a single grain, and hold it at arm's length against the night sky. The patch of darkness behind that grain is roughly the size of the region Hubble observed, and in that speck of apparent emptiness, the images revealed nearly 3,000 galaxies. 3,000 entire galaxies, each containing billions of stars, hiding behind what looked, to the naked eye, like nothing at all. Scaled up across the entire sky, those observations led scientists to estimate that the observable universe, the region of space we can actually see, contains something in the range of 200 billion galaxies. 200 billion. To put that in perspective, there are about 8 billion people on Earth. If you divided all those galaxies equally, among every person alive, each person would get 25 galaxies to themselves. Not 25 stars, not 25 solar systems, 25 entire galaxies, each containing hundreds of billions of stars, countless planets, and more mystery than we could ever explore. And every one of those galaxies, stretched across a universe roughly 93 billion light-years in diameter, seemed to fit perfectly within the predictions of the Lambda CDM model. The model was not just a theory, it was a framework confirmed by millions of measurements across every wavelength of light, from observatories on Earth and in space, over more than half a century of work. There is something quietly profound about what this model told us. When we look at distant galaxies, we are not seeing them as they are now. We are seeing them as they were when the light we are receiving left them, which, for the most distant galaxies Hubble observed, was billions of years ago. Every telescope is a time machine. Every photon of light that reaches our eyes is an old message, traveling toward us across an almost unimaginable distance. Looking out into space means looking backward through time. And when scientists looked backward through all that time with everything Hubble could offer, what they saw matched the story we had built. The universe grew more complex with age. The early universe was full of smaller, more primitive structures, just as the model predicted. The galaxies in the deep field images from the earliest epochs looked rougher, less organized, more diffuse. The evidence said The universe assembled itself slowly, piece by piece, across billions of years. You are part of that story. The carbon in your body, the iron in your blood, the calcium in your bones. Every atom was forged inside a star that lived and died before our own sun was born. You are not separate from cosmic history. You are made of it. The model, for all its mathematical complexity, ended with something deeply personal. Every one of us is assembled from material that passed through several generations of stars across billions of years of cosmic time. That was the universe we thought we understood. The lambda CDM model was not just compelling, it was, by every available measure, correct. Cosmologists were not uncertain about the broad outlines of cosmic history. They were confident. The age of the universe, the timeline of galaxy formation, the gradual assembly of structure from primitive beginnings, all of it rested on a foundation of evidence that had been tested from every angle imaginable. And so, in December of 2021, when NASA launched a new telescope into space, one powerful enough to look farther back in time than anything ever built, most scientists expected it to do what Hubble had done before it: confirm the model, fill in the remaining details, and give us sharper images of a universe we already understood. What it found instead would force some of the most careful minds in cosmology to sit very quietly and ask a question they had not seriously considered before. What if we had been looking at the wrong kind of light all along? The problem was not our models. The problem was not our mathematics. The problem was something far more fundamental and far more humbling. The universe was speaking to us in a language our instruments could not hear, and for decades we did not even know we were deaf. Every telescope ever built before the James Webb Space Telescope had the same invisible limitation. Not a flaw in the engineering, not a flaw in the science, a flaw in the nature of light itself and how the universe treats it over unimaginable distances. When a galaxy sits 13 billion light-years away, when the light from its stars has been traveling through expanding space for 13 billion years, something happens to that light along the way. The universe stretches it, pulls it. Like a sound from a car moving away from you, the frequency drops, the pitch lowers, until what was once the bright visible light of young hot stars arrives at our telescopes as something almost unrecognizable. Infrared, radiation, heat, a kind of light completely invisible to human eyes and largely invisible to every major telescope that came before. Hubble was brilliant, one of the most important instruments in the history of science. But when it came to seeing the very first galaxies, the ones from when the universe was only a few 100 million years old, Hubble was, in a very real sense, looking at the wrong colors. To see the beginning of the universe, we needed to build something entirely new. The phenomenon responsible for this is called redshift. The name is straightforward. As light travels across an expanding universe, its wavelength, the distance between the peaks of its waves, gets stretched. Shorter wavelengths correspond to bluer light. Longer wavelengths correspond to redder light. So as wavelengths stretch, the light shifts toward the red end of the spectrum. And for light that has been traveling for over 13 billion years, the stretching is so extreme that what started as ultraviolet or visible light arrives as infrared, light with wavelengths far longer than anything our eyes can detect. Picture this. Imagine sound waves from a musician playing across a room. As you move farther away, the sound waves that reach you have spread out and dropped in pitch. Now imagine the room itself is slowly expanding while you listen, every step of expansion tugging the sound waves slightly longer. Given enough distance, enough expansion, what started as a high note has become a low rumble you can barely feel. The universe does something almost identical to light, and the farther away the source, the more extreme the shift. So when scientists wanted to observe galaxies from the first few 100 million years of cosmic history, galaxies whose light left before our planet, before our sun, before most of the stars you can see tonight even existed, they needed a telescope designed to receive infrared light, not optical light. not ultraviolet, infrared, and they needed that telescope to be extraordinarily, almost impossibly sensitive. Hubble was not built for this. Hubble was optimized primarily for visible and ultraviolet light, the wavelengths that work brilliantly for observing stars and galaxies in our local universe, galaxies that haven't been traveling so long that their light has stretched beyond recognition. Hubble gave us breathtaking science, but the very oldest galaxies, the ones that formed when the universe was only a few % of its current age, were essentially invisible to it. They sat just beyond the horizon of what Hubble's instruments could reliably reach. Building a telescope that could reach beyond that horizon, that was the mission. The James Webb Space Telescope took roughly 25 years from initial concept to launch. A quarter of a century of design, engineering, disagreement, budget crises, delays, and extraordinary technical achievement. Its final cost came to approximately $10 billion, making it one of the most expensive scientific instruments ever constructed. That is not a number to pass over quickly. $10 billion invested in a single telescope, pointed at a universe that may or may not confirm our best theories about its own history. On December 25th, 2021, Christmas Day, the telescope launched from the Guiana Space Center in South America aboard an Ariane 5 rocket, and it began the most intricate deployment sequence ever attempted in space. Over the following weeks, Webb executed a series of over 300 critical steps, unfurling its sunshield, deploying its mirror, any one of which, if it failed, would have ended the mission entirely. Each step was performed at distances so great that radio signals took over 5 seconds to make the round trip. Engineers on Earth could not intervene in real time. The telescope had to execute the sequence itself, autonomously, with no margin for error. And it worked. Webb eventually settled into position at what scientists call the Sun-Earth L2 Lagrange point. That is a location in space where the gravitational pulls of the Earth and the Sun balance perfectly with the orbital motion of a spacecraft, creating a natural parking spot where a telescope can hover in stable alignment with almost no fuel expenditure. The L2 point sits 1.5 million kilometers from Earth. That is roughly 932,000 miles, or 37 times the circumference of our entire planet. Far enough from Earth that our planet's heat does not interfere with Webb's extraordinarily sensitive instruments. Far enough that our telecommunications systems can still reach it clearly, but not too far. The distance between Webb and Earth is close enough, relatively speaking, that light signals travel across it in about 5 seconds, which means that when the telescope sends back data, we receive it almost in real time by cosmic standards, and the data it began sending back was unlike anything that had come before. At the heart of the telescope sits a primary mirror unlike anything previously launched into space. 6.5 meters across, that is 21 feet, roughly the height of a 2-story building. For comparison, Hubble's primary mirror measures 2.4 meters, just under 8 feet. Webb's mirror is not simply larger, because mirror area determines how much light a telescope can gather, and area scales with the square of the diameter. Webb collects more than 7 times the light that Hubble can, 7 times more light, from sources 13 billion light-years away. The mirror is not one solid piece of glass. That would be impossible to launch. No rocket fairing is large enough to carry a single rigid mirror of that size. Instead, Webb's mirror consists of 18 separate hexagonal segments, each coated in an extraordinarily thin layer of gold. Not as decoration, gold is used because it is one of the most efficient reflectors of infrared light known to chemistry. Each segment is 1.32 meters across, about 4.5 feet, and together the 18 segments fold together like the petals of a geometric flower for launch, then unfurl in a line in space with a precision measured in nanometers, a nanometer being roughly 10,000 times thinner than a human hair. The alignment had to be that precise because even a small misalignment between segments would blur the images beyond usefulness. Engineers spent months guiding each segment into its exact position using a system of tiny actuators, small mechanical adjusters, until 18 separate mirrors became, in effect, one. Aboard Webb, 3 primary scientific instruments divide the work of seeing the early universe. NIRCam, the near-infrared camera, serves as Webb's main imaging system. It captures detailed pictures of objects in near-infrared wavelengths, which are just slightly longer than the red end of visible light. NIRCam is what produced Webb's first stunning deep-field images, revealing galaxies at distances that would have been unreachable by any previous telescope. NIRSpec, the near-infrared spectrograph, does something different and, in many ways, even more powerful. A spectrograph does not simply take a picture, it splits light into its component wavelengths and analyses the chemical fingerprint embedded within it, the way a prism splits white light into a rainbow, except NIRSpec can do this for hundreds of galaxies simultaneously. From that fingerprint, scientists can determine a galaxy's distance, its speed, and even the chemical composition of the stars inside it. Age, mass, element content, revealed by the structure of light alone. And MIRI, the mid-infrared instrument, reaches even further into the infrared spectrum, seeing wavelengths of light so long and so faint that the instrument itself must be cooled to -266 degrees Celsius, just 7 degrees above the absolute coldest temperature that physically exists in the universe. At that temperature, MIRI's own heat is reduced to almost nothing, so it does not accidentally detect itself instead of the distant galaxies it is searching for. Here is what all of this engineering actually means in human terms. When you look at a star, you are not seeing it as it is now. You are seeing it as it was when the light you are receiving left it. For nearby stars, this delay is modest, a few years, perhaps a few hundred. For stars in distant galaxies, the delay becomes immense. And for the galaxies Webb was built to see, the light has been travelling so long that what we receive today is a snapshot of a universe that no longer exists in that form. Consider this carefully. Webb can detect light from galaxies roughly 13.5 billion light-years away. That light left its source 13.5 billion years ago. At that time, our sun had not formed. Earth had not formed. The solar system did not exist. The light now reaching Webb's golden mirror left a young, turbulent universe nearly 9 billion years before our planet was even born, and it has been travelling ever since, through the expanding void, waiting to arrive at a mirror that would not exist for most of cosmic history. You are, in a real and measurable sense, looking at the ancient past of the universe every time Webb sends back a new image, not a reconstruction of the past, not an artist's impression, an actual photograph taken with actual light from that actual moment in time. That is what the engineers and scientists built, a time machine, not in the science fiction sense, but in the only sense that actually works in physics, an instrument precise enough, cold enough, large enough, and sensitive enough to receive messages sent by the universe from an era when life, planets, and stars like our own sun had not yet come into existence. The telescope arrived at L2, its 18 golden segments aligned, its instruments cooled to within a few degrees of absolute zero, and in the summer of 2022, scientists released the first full-colour images from James Webb. The scientific community had waited 25 years for this moment. They had high hopes, but also carefully calibrated expectations. The models predicted what they should find: a distant universe full of small, faint, primitive galaxies. The early universe was supposed to be a rough sketch, not a finished painting. And then the data came in. What the first images revealed was not what the models predicted, not slightly off, not a minor revision. The galaxies in those earliest images were not small, they were not faint, they were not primitive. And scientists, quietly, began to wonder if the story they had spent decades building might be missing something important. The image appeared on screens around the world on July 12, 2022, and the scientists who had spent years building the telescope stared at it in silence. Something was not right. Something was far, far too bright, and no one in the room knew what to do with that. The data had been sitting in the computers for weeks before anyone saw the final processed image. Webb had been collecting light, instrument by instrument, pixel by pixel, recording infrared signals from a corner of the sky so small, so apparently empty, that no ordinary telescope would have bothered pointing at it. And then, on July 12, 2022, NASA released the first full deep-field image to the world. What appeared on those screens was not what the models had predicted, not slightly off, not a minor discrepancy that statisticians would argue about for months before reaching a consensus. The image showed galaxies, hundreds of them, layered across the frame like light scattered through, a window at distances and brightnesses that the best cosmological models said should not be there. Not yet, not at that age. Scientists did not immediately announce a crisis in cosmology. That is not how science works. The first response, professionally and appropriately, was suspicion. Something must be wrong with the data. Something must be wrong with the instruments. The universe had spent billions of years confirming the model. Surely it would not shatter it in a single photograph. But it had. To understand why the images were so shocking, we need to understand what Webb was supposed to find. The cosmological model, built on decades of Hubble observations, mathematical simulations, and deep theoretical work, made very specific predictions about what the early universe should look like. The prediction was this: the earliest galaxies, the ones that formed within the first billion years of cosmic history, should be small, faint, primitive, rough structures of gas and young stars, barely organized, nothing like the grand spiral and elliptical galaxies we see in the nearby universe today. The universe needs time to build complexity. Galaxies need billions of years to grow massive, to accumulate stars across countless mergers, to build up the heavy elements that only form inside stars over generations. The first galaxies should look, in the model, like rough sketches compared to the finished paintings we see nearby. This expectation was not wishful thinking. Hubble had confirmed it to the extent that Hubble could see. The faintest, most distant galaxies visible to Hubble did appear small and irregular. The model held, and Webb was expected to simply see farther back along the same trajectory, finding galaxies that were even smaller, even fainter, even more primitive, from even earlier in cosmic time. Scientists were confident. The prediction seemed safe. The first deep field image Webb released was centered on a galaxy cluster called SMACS 0723. A galaxy cluster is exactly what it sounds like: a region of space where hundreds or even thousands of galaxies have gravitationally gathered together into a single enormous group. Scientists chose this particular cluster as Webb's first deep field target because it acts as a natural gravitational lens, meaning the combined mass of all those galaxies bends and magnifies the light from even more distant galaxies behind it, like a giant cosmic magnifying glass floating in space. The field of view Webb captured was extraordinarily small. Picture this. Hold a grain of sand at arm's length against the night sky, and the patch of darkness behind it is roughly the size of the region Webb photographed. That is it, a grain of sand's worth of sky. And within that almost invisibly small patch of darkness, the image revealed thousands of individual galaxies, some nearby, some at moderate distances, and some from so far away that their light had been traveling for over 13 billion years before reaching Webb's golden mirror. That light had been traveling longer than our solar system has existed, longer than Earth has existed. When some of those photons left their source, the region of space where our sun would eventually form was not yet even a cloud of gas. How do scientists know how far away a galaxy is? They measure its redshift. A galaxy's redshift, the degree to which its light has been stretched to longer, redder wavelengths by the expansion of the universe, directly encodes how long that light has been travelling. The higher the redshift, the more the light has stretched, and the older and more distant the source. Webb's instruments can detect redshifts far higher than Hubble could reliably reach, allowing scientists to identify galaxy candidates from the first few 100 million years of cosmic time. And this is where the first surprise arrived. Scientists began identifying galaxy candidates at redshifts higher than anything previously confirmed. Some appeared to be from less than 500 million years after the Big Bang. To calibrate how early that is, if you compress the entire 13.8 billion year history of the universe into a single calendar year, 500 million years would represent 13 days. The universe would be 13 days old, not yet 2 weeks into its existence, and already forming galaxies that Webb could see clearly. But the age was only part of the problem. The real shock was the brightness. The model predicted that galaxies from this era should be faint. They should require deep, extended observations to detect at all. They should be ghostly, barely distinguishable from background noise. Instead, the galaxies Webb detected at these extraordinary distances were remarkably puzzlingly, in some cases almost inexplicably bright. Some appeared to be producing light at rates that seemed inconsistent with the limited time available to them. If a galaxy forms at 300 million years after the Big Bang, how does it already contain enough stars, enough stellar mass, to shine so powerfully? The model had an answer for this question. The answer was, it does not. A galaxy that young, according to everything we understood about how galaxies grow, should not be that luminous. Star formation takes time. Mass accumulates gradually. The early universe simply had not been running long enough to produce galaxies this bright. And yet there they were. Dozens of them. Across the very first image Webb returned. Astronomer Garth Illingworth, one of the scientists who helped design Webb's imaging strategy, later described the reaction of the team when the first candidate galaxies at extreme distances were confirmed. The instinct was not excitement. The instinct was to check everything, to look for contamination in the data, to search for instrument artifacts, false signals introduced by the telescope itself, to run the analysis again and again and again, looking for the mistake that must have produced such an impossible result. This is what careful science looks like from the inside. Not immediate celebration, methodical, disciplined suspicion of your own data. The universe had offered an extraordinary claim. The scientists demanded extraordinary verification before they would accept it. What happened to those suspicions? The same thing that always happens when a mystery is real rather than instrumental. The more carefully scientists checked, the more robust the findings became. The candidate galaxies survived multiple rounds of analysis. The photometric redshifts, the initial distance estimates based on how the galaxy's colours shifted across Webb's different filters, were consistent, and when follow-up spectroscopic observations began confirming individual galaxies, measuring their precise distances by analysing the chemical fingerprints in their light, the candidates held up. The bright early galaxies were not artifacts, they were not measurement errors, they were real, and they were more numerous than the models predicted, not by a small margin, not by the kind of modest overshoot that could be explained by fine-tuning a parameter or two. The early universe appeared to contain significantly more bright, massive galaxies than our best simulations said it should. Something was missing from the model. Something important. How do you explain galaxies that should not exist yet? Galaxies that are too bright, too massive, too structured for their age? What process could accelerate cosmic construction so dramatically that the universe built in a few 100 million years what the model said should require billions? The meaning of those first deep field images only becomes fully clear when you hold both facts in your mind at once. On one side, a model built over decades, tested in every way we knew how to test it, confirmed by Hubble and by ground-based observatories and by satellites, measuring the faint afterglow radiation of the Big Bang itself. On the other side, a set of images from the very first months of Webb's operation, showing galaxies from an era when those galaxies, by rights, should barely have begun to form. You do not need to understand the mathematics to feel the weight of this. If the universe was 13 days old, in our compressed year analogy, when some of these galaxies formed, and if those galaxies were already substantially massive and luminous, then the universe was assembling complex structure at a pace no one had calculated. The construction of the cosmos was happening faster than we thought, and the implications of that speed were only beginning to come into focus. The first images were not a final verdict. Science does not work that way, but they were, unmistakably, a disturbance, a signal that the story we had told about cosmic history was, at minimum, incomplete, and possibly wrong in ways that no one had anticipated. Initial wave of Webb deep field data raised questions that the scientific community would spend the following months and years trying to answer. Some argued for revised parameters within the existing model. Others raised the possibility of entirely new physics. The debate was real and productive and ongoing. But before any of that debate could be settled, Webb began finding something even stranger than unexpectedly bright early galaxies. Not just galaxies that formed a little earlier than expected. Not just galaxies that were a little more luminous than the models allowed. What came next were objects so massive, so structured, so seemingly impossible for their age, that some researchers reached for a word that scientists rarely use about an observation: impossible. Scientists had a name for what Webb was supposed to find at the edge of the observable universe. Primitive. That was the word built into the models. Small, faint, primitive. Not yet complex, not yet massive. The first galaxies, according to everything we understood, were supposed to look like rough beginnings. Webb found something else entirely. The universe was 300 million years old when some of these galaxies existed. Sit with that for a moment. 300 million years sounds large, but the universe is 13.8 billion years old. 300 million years is roughly 2% of its entire history. If you compressed cosmic time into a single calendar year beginning on January 1st, these galaxies formed on the 8th of January, 8 days into the year, before the universe had even finished its first week by that measure. And yet, Webb found galaxies there, real ones, confirmed, massive, luminous, structured. Nothing in the model predicted this. Much of what we know about this extraordinary period in cosmic history comes from a dedicated observational campaign called JDS, the JWST Advanced Deep Extragalactic Survey. Extragalactic simply means beyond our own galaxy, observations of the universe outside the Milky Way. JDS was designed from the beginning to push Webb to its limits, staring deep into small patches of sky for extended periods to collect as much ancient light as possible. The survey targeted a region of sky that astronomers had studied before, a patch made famous by the Hubble Space Telescope's own deep field observations. But Webb's infrared sensitivity allowed it to reach back through distances, and therefore through time, that Hubble could not reliably access. And what emerged from those observations rewrote the earliest chapter of cosmic history. Among the confirmed discoveries, a galaxy designated JD's GSZ130. The name is scientific notation, but the significance is straightforward. This galaxy existed when the universe was approximately 320 million years old. Its light has been traveling toward us for roughly 13.5 billion years, more than 3 times the age of our entire solar system, and when it finally reached Webb's golden mirror, what the data revealed confounded the predictions. Here is why this matters so deeply. A galaxy's mass, the total mass of all the stars within it, is not something that accumulates instantly. Stars form from collapsing clouds of gas, and that process takes time, millions of years per generation of stars. Then those stars age, explode, scatter their material back into space, and the next generation forms from the enriched remnants. Building up billions of stars across a galaxy is a process measured in billions of years. That is what the model said. That is what every simulation confirmed. The Milky Way, our own galaxy, contains roughly 60 billion times mass of our Sun in stars alone. It took billions of years of continuous star formation to accumulate that mass. 60 billion solar masses built up across most of the history of the universe. Now consider what JWST found at redshifts above 10, redshifts corresponding to the first few 100 million years of cosmic time. Some galaxy candidates showed stellar masses already reaching into the billions of solar masses, several billion times the mass of our Sun, assembled within roughly 300 to 500 million years of the Big Bang. That is approximately 17 times faster than the standard model predicted galaxies of that mass should be able to form. Not slightly ahead of schedule, 17 times ahead of schedule. To understand why those numbers are so troubling, we need to understand how the model says galaxies are supposed to grow. The accepted picture goes like this. After the Big Bang, the universe filled with hydrogen gas distributed almost, but not, perfectly, uniformly through space. Small variations in density existed, regions that were infinitesimally denser than others. Gravity amplified those variations over millions of years, pulling gas slowly into denser knots, which attracted more gas, which collapsed further, which eventually formed the first stars. Those stars clustered into the first small galaxies. Those small galaxies then merged, over hundreds of millions to billions of years, into larger ones. The key word is gradually. The process is constrained by physics. Gas can only fall inward so fast. Stars can only form from gas that has had time to cool and collapse. The rate at which a galaxy can convert raw gas into stars has limits. And those limits, written into the mathematics of the standard model, said that a galaxy reaching several billion solar masses in less than 500 million years should be extraordinarily rare. Not impossible, but vanishingly rare. Webb found them, not one, not a handful, multiple, confirmed galaxies, and many more candidates awaiting final confirmation from this impossibly early era, with masses that the model said had no business existing yet. How do you build something in 8 days that the blueprints say takes a year? The deeper puzzle sits inside the question of star formation efficiency. In our universe today, most of the gas in a galaxy does not actually form stars. Only a small fraction, a few percent, of a galaxy's available gas gets converted into stars in any given period. The rest stays as gas, or gets blown outward by the energy of supernovae and stellar winds. This low efficiency is actually why galaxies like the Milky Way still have gas available to form new stars today. The process is slow and wasteful by cosmic standards. Picture this. Imagine a factory that receives 100 tons of raw material every week, but converts only 3 tons into finished products. That is roughly analogous to how star formation works in galaxies like ours. Most of the raw material just sits there, or gets ejected from the building entirely. For the early galaxies Webb found to reach their observed masses as quickly as they apparently did, that efficiency would need to have been far higher than anything seen in the modern universe. Not 3%, potentially 30, 40, or even higher, with almost all of the available gas being converted into stars at a pace unlike anything we observe today. Some researchers have argued this is physically plausible under the extreme conditions of the early universe, when gas was denser and the environment more turbulent. Others remain deeply skeptical. This is one of the most genuinely contested questions in modern cosmology right now, and it does not have a settled answer. It is worth pausing here to address the question that careful thinkers will naturally raise. Could these detections be wrong? Could the distance estimates be mistaken, placing galaxies at extreme redshifts that they do not actually occupy? Initially, Almost all the early galaxy candidates were identified using photometric redshifts, distance estimates based on how a galaxy's light distributes across different color filters. A galaxy at extreme distance shows up only in the reddest infrared filters, invisible to bluer ones because all its visible light has been stretched far into the infrared. Scientists use this color pattern to estimate distance, but it is an estimate, a proxy. It can occasionally be fooled by unusual objects at much closer distances that mimic the color signature of distant ones. Spectroscopic confirmation, actually splitting the galaxy's light into its detailed spectrum and measuring precise chemical fingerprints, is the gold standard. And as Webb's near-spec instrument turned toward the most compelling candidates, confirmation after confirmation held. The spectroscopic redshifts match the photometric ones. JD's GSZ130 is genuinely at the distance it appears to be. Other galaxies in the JDA survey have been confirmed at redshifts above 10, above 11, above 12. These objects are real, they are ancient, and they are more massive than the model said they should be. The discovery of galaxies at 300 million years, confirmed, massive, luminous, does not simply mean the universe formed a few galaxies a bit earlier than expected. The implications run deeper than that. If galaxies of substantial mass already existed at 300 million years after the Big Bang, then the gas that formed their stars must have collapsed extremely efficiently, extremely quickly, under conditions we do not fully understand. That means the large-scale structure of the universe, the gravitational scaffolding that dark matter provides, the filaments and nodes along which gas flows and galaxies assemble, must have organized itself faster than our simulations suggest. You are not simply looking at a few unexpectedly early galaxies when a Webb shows you these objects. You are potentially looking at evidence that the entire timeline of cosmic construction needs to be revised. The early universe was not slowly assembling rough sketches in the dark. Based on what Webb found, it appears to have been working at a pace that our models had not accounted for. The question that every simulation team and every cosmological theorist now wrestles with is, what drove that pace? What mechanism accelerated the universe's construction schedule so dramatically in those first few 100 million years? And when you look at those ancient galaxies in Webb's images, those faint, impossibly distant smears of light, you are looking at places where 9 billion years before our planet existed, billions of stars had already been born, lived their lives, and in many cases already died. The atoms forged in those stars drifted through space for billions of years. Some of them, eventually, found their way into the cloud of gas that became our sun, and then, further still, into you. The JD's galaxies raised the pace of the puzzle considerably, but the discoveries did not stop there. Even as scientists worked to understand how galaxies of that age could be so massive, Webb began revealing something stranger, still lurking among the first billion years of cosmic time. Not just early galaxies that were larger than expected, galaxies so extraordinarily massive, so heavily populated with stars, that some researchers began calling them by a name that captured both their size and their strangeness: the red monsters. And unlike anything seen before in the early universe, they appeared to rival some of the largest galaxies that exist today, formed, somehow, in an era when the universe had barely begun. Astronomers have a rule of thumb. The early universe was supposed to be small, modest, still assembling itself. So when a team of researchers sifted through the first months of Webb data and found objects that appeared as large as some of the biggest galaxies in today's universe, sitting in an era when the universe was barely 5% of its current age, they gave those objects a name that captured exactly how they felt about them. The universe grows more complex with time. That was one of the most thoroughly tested ideas in cosmology. Larger galaxies are built by smaller ones merging over billions of years. The earliest galaxies should therefore be the smallest and least evolved. That logic was not wishful thinking. It was the direct, mathematically rigorous prediction of the best cosmological models ever constructed, confirmed across decades of observation. And then, in early 2023, a study published in the journal Nature presented data from 6 galaxy candidates found in Webb's first images, candidates sitting roughly 600 to 700 million years after the Big Bang. And the stellar mass estimates attached to some of those candidates were staggering, not slightly larger than expected, not modestly ahead of schedule. Some of these objects, if the mass estimates held, appeared to contain roughly as many stars as our own Milky Way, or more. Assembled in a universe less than 5% of its current age, scientists called them the red monsters, and the name was earned. The name requires a moment of explanation, because understanding why these galaxies appear red is actually key to understanding why they are so extraordinary. When astronomers look at nearby galaxies, younger stars tend to be blue-white and intensely hot. Older stars, stars that have burned through most of their hydrogen and swelled into cooler, larger forms, glow red and orange. A galaxy dominated by old stars, therefore, appears redder than one, still actively forming new blue ones. The red color of these ancient galaxies tells us something profound. By the time their light left them, they already harbored old stellar populations. Stars that had been burning long enough to age. Not young, freshly lit fires, but mature, cooling ones. Add to that the effect of cosmic redshift, which stretches their light further toward the infrared, and the dust within these galaxies, which absorbs shorter wavelengths and allows longer ones to pass. And what reaches Webb's mirror is a deep, warm glow from objects that are ancient in every sense the word carries. Red, massive, and, according to the models, impossible. The Milky Way, our own galaxy, home to somewhere between 200 and 400 billion stars, has taken roughly 13 billion years to accumulate its current stellar mass. 13 billion years of star formation, stellar deaths, gas recycling, mergers with smaller galaxies and gradual accretion. The result is a galaxy containing roughly 60 billion times the mass of our Sun in stars. 60 billion solar masses built across nearly the entire history of the universe. Now consider the timeline facing the red monsters. These objects existed when the universe was approximately 600 to 700 million years old. That is roughly 19 times faster than the Milky Way assembled comparable mass. To achieve a stellar mass rivaling our entire galaxy in that window, the average rate of star formation would need to have been around 30 times higher than the Milky Way manages today. 30 times more stellar mass being born every year, sustained continuously for hundreds of millions of years. That number sounds large. It is large. But here is what makes it genuinely troubling to cosmologists. The models say it is not just unlikely. It pushes against the physical limits of how quickly gas can collapse, cool, and ignite into stars under known conditions. The universe, by standard physics, simply should not have been able to build these objects that fast, not without something fundamentally different occurring in the early universe, something our models are not currently equipped to describe. But the mass problem is only half of it. The chemistry makes the situation stranger still. When the universe began, only 3 elements existed in meaningful quantities: hydrogen, helium, and trace amounts of lithium. Every other element in the periodic table, every atom of carbon, oxygen, nitrogen, iron, silicon, was forged later inside the cores of stars and released into space when those stars exploded as supernovae. Astronomers call all elements heavier than helium metals, which is their technical shorthand for everything the universe built after the Big Bang. The first stars, called population 3 stars, contained none of these metals. 0. They were made of the raw material of the Big Bang alone. The second generation of stars, seeded by the expelled material of those first explosions, contained a small amount of heavier elements, and successive generations added more. The process is slow. each stellar generation requiring millions of years to live, explode, and enrich the surrounding gas for the next cycle. Picture this. Imagine a recipe that requires an ingredient that only one factory in the world produces. That factory only opens after the previous factory has finished operating and closed, which takes 5 to 10 million years per cycle. To accumulate enough of that ingredient to fill a kitchen requires dozens of factory cycles, one after another. Now, imagine someone hands you a finished cake and tells you it was baked in 700 million years. You would immediately ask, how many factories ran, and how fast did they operate? That is exactly the question facing astronomers when they analyze the chemical composition of the red monsters. Several candidates show levels of heavy elements, metals, in the astronomical sense that suggest the gas in these galaxies had already passed through multiple generations of stars by the time their light left them. Multiple generations of stars being born, burning through their fuel, exploding, and seeding the next generation, all within a window that the models considered barely sufficient for the first generation to even begin. How do you compress multiple stellar lifetimes, multiple cycles of cosmic chemistry, into a universe that has barely had time to strike its first match? In February 2023, astrophysicist Ivo Labbé of Swinburne University, who led the nature study that first formally characterized these objects, described the reaction of the research team when they processed the mass estimates. The team ran the analysis expecting to find galaxies with modest masses, objects consistent with standard model predictions. What appeared in the data instead were objects so much larger than expected that the initial response was, in his own words, disbelief. They went back through the calculations repeatedly, looking for the error that must have produced such an anomalous result. But the numbers held, the objects were real, and if the mass estimates were accurate, they represented a direct challenge to the standard model of galaxy formation. This is what a genuine scientific discovery feels like from the inside. Not triumph, suspicion, then reluctant, careful, mounting acceptance. A fair account of the red monsters requires acknowledging what came next. Following the initial Nature paper, spectroscopic follow-up observations, the more precise, definitive measurements that confirm or revise photometric estimates, began narrowing some of the mass figures downward. Some candidates turned out to be somewhat less massive than the early color-based estimates suggested. Some light originally attributed to stellar mass appeared to have contributions from active galactic nuclei, the intense radiation produced by supermassive black holes at galaxy centers, which can mimic the signatures of enormous stellar populations. So, the debate is genuinely open. Some researchers argue that even the revised, lower mass estimates still challenge the model significantly. Others suggest that a combination of revised physics parameters, higher star formation efficiencies in the early universe, different dust properties, contributions from black hole activity, might reconcile the observations with the existing framework without requiring new fundamental physics. Neither side has won. The tension remains, and the honest answer is that we do not yet know, with certainty, precisely how massive these objects are, or precisely what mechanism produced them. What we do know is that they exist, and that their existence means the early universe was doing something our models had not fully anticipated. Step back and consider what the chemistry evidence implies, if taken seriously. The presence of significant heavy elements in galaxies from 600 to 700 million years after the Big Bang means that somewhere inside those galaxies, stars had already been born, had burned for millions of years, had collapsed and exploded, had scattered their enriched material back into the surrounding gas, and that gas had then cooled, collapsed again, and formed a new generation of stars, all within the first tiny fraction of cosmic history. Those stars are long gone. They burned out billions of years before our sun ignited. But the atoms they forged, carbon, oxygen, iron, became part of the gas that later formed newer generations of stars. And those later generations across billions of years of subsequent history, contributed their own enriched material to the interstellar medium of their galaxies. Some of that material, drifting through space across unimaginable timescales, eventually found its way into the molecular cloud that collapsed to form our solar system. You carry in your own body atoms that were processed through stars that lived and died in the universe's first billion years. The red monsters are not just a puzzle for cosmologists, they are part of your own chemical lineage. The red monsters raised a question that cut to the heart of how the early universe functioned. If galaxies this massive, this chemically enriched, this structurally developed, could exist in the first billion years, what else was the early universe building that we had not anticipated? The red monsters were remarkable for their stellar mass, but sitting at the center of many of the most massive early galaxies, feeding on the surrounding gas, and in some cases contributing to the extraordinary brightness that first caught Webb's attention, were objects even more perplexing. Supermassive black holes. Ancient ones. Black holes so large, detected so early in cosmic history, that they should not have had time to grow to the sizes Webb was finding them, and the physics of how they got there was something no model had cleanly explained. At the center of our galaxy, roughly 26,000 light-years from where you are sitting, a black hole called Sagittarius A star sits in almost perfect silence, 4 million times the mass of our Sun, compressed into a space smaller than our solar system. Enormous, ancient, and, as Webb is now revealing, not remotely the most extreme example the universe has produced. After the first months of Webb data, cosmologists faced a difficult but manageable problem. Early galaxies were more massive and more luminous than predicted. Unsettling, certainly. Enough to prompt vigorous debate and revisions to existing simulations, but not necessarily a catastrophic failure of the underlying model. Perhaps star formation efficiency had been underestimated. Perhaps the early universe's gas conditions were different in ways the simulations had not fully captured. The galaxies were anomalous, but not inexplicable. Then Webb began detecting what was powering some of those galaxies from within. Supermassive black holes. Not the modest kind, not objects comparable in size to the one at the center of our own Milky Way. Objects measuring hundreds of millions, or in some cases, over 1 billion times the mass of our Sun, existing within the first 500 to 700 million years of cosmic history. And the physics of how they got that large, that fast, had no clean answer in any model anyone had built. A black hole is a region of space where so much mass has collapsed into such a small volume that the gravitational pull becomes strong enough to trap even light. Once something crosses the boundary, called the event horizon, nothing escapes. Not matter, not radiation, not any signal of any kind. Supermassive black holes are the giants that reside at the centers of most large galaxies. The one at the center of our galaxy, Sagittarius A star, contains roughly 4 million times the mass of our Sun, compressed into a sphere roughly the size of our solar system, about 20 to 25 times the distance from Earth to the Sun across. That is already a staggering amount of mass in a small space. But the black holes Webb began detecting in the early universe were not in that category. Some measured hundreds of millions of solar masses. One well-documented example, a quasar designated J0313-1806, carries a black hole of approximately 1.6 billion solar masses. A quasar is a type of extremely luminous object, powered by a black hole actively consuming enormous quantities of surrounding material, making it visible across vast distances. And this one existed when the universe was approximately 670 million years old. 1.6 billion solar masses, 400 times more massive than the black hole at the center of our entire Milky Way, and it had assembled itself in less time than it took our solar system to form. Here is the fundamental physical problem. Black holes grow by consuming matter. Gas, dust, and debris fall toward the black hole, heat to extreme temperatures as they spiral inward, and radiate enormous quantities of energy. That is the light we see from quasars. But this very radiation creates a counterpressure. As a black hole consumes matter and radiates energy outward, that outward radiation pushes back against the infalling gas, slowing and eventually halting further consumption if the accretion rate becomes too high. The maximum rate at which a black hole can sustainably consume mass, given this radiation pressure balance, is called the Eddington limit. Named for the British astrophysicist Arthur Eddington, it defines a ceiling. A black hole can only eat so fast before its own energy output blows its food supply away. And at that maximum rate, at continuous, uninterrupted Eddington accretion, a black hole roughly doubles its mass approximately every 45 million years. 45 million years per doubling it. The absolute theoretical maximum. Now consider the problem. Let us walk through the numbers together, because this is where the mystery becomes tangible. A typical stellar black hole, the kind that forms when a massive star collapses, starts at roughly 10 solar masses. That is the seed. To grow from 10 solar masses to 1 billion solar masses requires a growth factor of 100 million times. Starting at 10, doubling to 20, then 40, then 80. Doing that continuously requires roughly 27 doublings to reach 1 billion solar masses. 27 doublings at 45 million years each. Even at the absolute Eddington limit, faster than black holes can physically sustain in practice. That process requires somewhere in the range of 800 to 1200 million years. But J0313-1806 existed at 670 million years after the Big Bang. The entire age of the universe at that point was shorter than the time needed to grow the black hole that sits inside it, even under the most optimistic physical assumptions. The math does not work. The time simply was not there, and this was not an isolated case. In 2024, a team led by Roberto Maiolino of Cambridge University published observations in the journal Nature confirming a supermassive black hole inside a galaxy called GNZ11. GNZ11 is one of the most distant confirmed galaxies known. Its light left when the universe was approximately 430 million years old. 430 million years. At that point in cosmic history, most of the stars in the Milky Way had not been born. The Sun was more than 9 billion years away from existing, and sitting at the center of this extraordinarily ancient galaxy, Maiolino's team found a black hole actively consuming surrounding material. A black hole with a mass of roughly 1.5 million solar masses already feeding at, or above the Eddington limit, already growing at the fastest physically permissible rate. Picture this. Imagine arriving at a construction site and finding a building that should have taken 10 years to construct standing fully completed after only 3. You would not simply adjust your estimate of construction speed. You would start asking whether the building had been built using methods you had not previously known existed. That is where astrophysicists now stand with these ancient black holes, not slightly puzzled, fundamentally rethinking the origin story. Scientists have proposed 2 main pathways that might explain how black holes this massive could exist so early, and both are genuinely extraordinary. The first is super Eddington accretion, the idea that under the extreme gas-rich conditions of the early universe, black holes may have been able to consume matter faster than the standard Eddington limit allows. Not forever, not continuously, but in short, intense episodes, eating at rates 2, 5, or even 10 times the theoretical maximum before the radiation pressure temporarily disrupted the infalling material. Some theoretical models support this possibility. Others argue the physical conditions required are too extreme to be widespread. The second explanation is more radical and in many ways more elegant: direct collapse black holes. Rather than starting from the 10 solar mass remnant of a single dead star, these objects may have formed through a completely different mechanism: enormous clouds of primordial gas tens of thousands to hundreds of thousands of solar masses in size, collapsing directly into a black hole in a single catastrophic event, bypassing the star formation stage entirely. A direct collapse black hole starts hundreds of thousands of times more massive than a stellar remnant, which dramatically reduces the number of doublings needed to reach 1 billion solar masses within the available time. Both mechanisms remain hypothetical, in the sense that neither has been definitively observed in action. Both have theoretical support, and both require conditions that the standard cosmological model did not predict as common features of the early universe. The honest answer is, we do not currently know which mechanism, if either, is the dominant explanation. This is a genuine, open, unresolved question in modern astrophysics, and the data Webb is continuing to collect will likely be central to answering it. What makes the ancient black holes discovered by Webb particularly significant is not just their size, it is their relationship to the galaxies around them. In the modern universe, the mass of a galaxy's central black hole and the mass of its central stellar bulge, the dense ball of old stars at a galaxy's core, track each other with remarkable precision. Bigger bulge, bigger black hole, smaller bulge, smaller black hole. This tight relationship suggests that galaxies and their central black holes grew together, each influencing the other over billions of years. The black hole's energy output, when it is actively feeding, can heat and expel gas from the surrounding galaxy, regulating how many new stars form. The galaxy's gas supply, in turn, determines how fast the black hole can grow. But in GNZ11, and in objects like J0313-1806, the black hole appears to be extraordinarily massive relative to the galaxy around it. Far more massive, proportionally, than the tight relationship seen in the modern universe would predict. Which raises a question that cuts to the heart of how structure assembles in the cosmos. Did the black hole form first, and the galaxy grow around it? Or did something about the extreme conditions of the early universe temporarily decouple the growth rates that are so tightly linked in the universe today? You might not think the life history of a black hole 13 billion light-years away has anything to do with you, but the carbon in your body, the calcium in your bones, the iron in your blood, all of it passed through stars that lived inside galaxies that were shaped, in part, by the black holes at their centers. The growth history of ancient black holes is, in the deepest sense, part of the history of every atom that makes you up. Massive early galaxies, ancient red monsters, supermassive black holes that grew faster than physics easily allows. Each discovery, taken alone, might be explained by some adjustment to the standard model, an unusually efficient period of star formation, a different gas environment in the early universe, special seeds for early black holes. But Webb was not finding one anomaly. Webb was finding a pattern. And the deeper question, the one that all of these discoveries were beginning to force onto the table, was not simply whether individual objects were more massive than expected. The question was whether the entire early universe was more densely populated, more extensively structured, more thoroughly organized than the models had ever suggested. Not just a few surprising objects scattered across the early cosmos, but a universe that, from its very first billion years, appears to have been far more crowded and far more active than anyone had calculated. Every number we had ever used to describe the population of the universe turned out to be an undercount. Not because the instruments were bad, not because the mathematics was wrong, because we had been looking at the sky the way someone looks at a dark room with a single candle, and calling it empty. For most of human history, the universe seemed sparse. The naked eye can see roughly 5,000 stars on a clear night. A modest telescope revealed millions more. Larger telescopes pushed that to billions. And then, over the course of the 20th century, astronomers began to understand that what we were counting as individual stars were in many cases entire galaxies, vast cities of hundreds of billions of stars each, sitting at distances so great that even the best instruments rendered them as single points of faint light. That revelation alone should have been humbling enough to last generations. And then Hubble pointed at a dark patch of sky and found 3,000 galaxies behind a grain of sand's worth of darkness. And the census expanded again. 200 billion galaxies, scientists estimated, filling the observable universe in every direction. That number, 200 billion galaxies, stood for years as our best accounting of the universe's population. Tested, modelled, defended. Webb looked more carefully, and the number is almost certainly wrong. The estimate of 200 billion galaxies came from Hubble's deep field surveys and careful extrapolation. Hubble could see galaxies out to a certain distance, count them in small patches of sky, and project that count across the entire sky. The method was sound. The result was staggering. But Hubble had a limitation that was not a flaw in the engineering. It was a limitation of physics. Hubble's sensitivity was concentrated primarily in visible light. Galaxies at extreme distances, whose light had been stretched far into the infrared by billions of years of cosmic expansion, were largely invisible to it. The surveys Hubble conducted were sampling only the portion of the universe's galaxy population whose light happened to fall within the wavelengths Hubble could detect. In 2016, a team led by astronomer Christopher Consolis at the University of Nottingham published a more comprehensive estimate in the Astrophysical Journal. Using mathematical modelling to account for the faint, distant galaxies that even Hubble could not see, they concluded that the observable universe likely contains not 200 billion, but approximately 2 trillion galaxies. 2 trillion, 10 times the previous estimate, and most of those additional galaxies were small, faint, and invisible to any instrument that came before Webb. 2 trillion galaxies. Let us sit with that number for a moment. Imagine you decided to count every galaxy in the observable universe at a rate of 1 per second. No stopping, no sleeping, just counting continuously. 1 galaxy per second. How long would that take? Walk through the arithmetic. 2 trillion seconds divided by approximately 31.5 million seconds per year comes to roughly 63,000 years. 63,000 years of continuous counting to name every galaxy we can observe. 63,000 years ago, modern humans were living in small groups across Africa and Eurasia. The last ice age had not yet peaked. Writing would not be invented for another 55,000 years. Agriculture was 60,000 years in the future. All of recorded human history, every civilization, every empire, every text ever written, fits within the last 5,000 of those 63,000 years. That is a staggering count. And Webb suggests that even that staggering count is an underestimate. When Webb began returning deep observations of the early universe, researchers comparing the galaxy populations at extreme distances to what Lambda CDM predicted found something profoundly unsettling. The number of bright, massive, luminous galaxies in the first billion years of cosmic history exceeded the model's predictions by factors of tens, and in some analyses, for the very brightest objects, by factors approaching 100. Not 10% more, not twice as many. Studies published in the Astrophysical Journal Letters and other major journals between 2022 and 2024 consistently found that the density of UV bright galaxies at redshifts above 10, meaning from before the universe was 1 billion years old, was far higher than any simulation had generated. 100 times more bright early galaxies than expected, in a universe that was supposed to still be assembling its first rough structures. Here is what makes this finding particularly striking when you consider it geometrically. At redshift 10, when those distant galaxies existed, the universe had expanded to only about 9% of its current linear scale, and volume scales with the cube of that expansion. So the volume of the observable universe at that epoch was only about 1/13 of 1% of its current volume. The universe at that time was more than 1,000 times more compact than it is today. Picture this. Take everything in the observable universe, every galaxy, every filament of dark matter, every knot of gas, and compress it into a ball roughly 1/13 of 1% of its current size. That is the universe these early galaxies inhabited. A universe already containing far more luminous, massive structures than we expected, packed into a space dramatically smaller than the cosmos we observe today. The early universe was not a sparse, slowly awakening landscape. Based on what Webb is revealing, it appears to have been a dense, intensely active environment where construction was already well underway, and where the population of bright, massive objects was already far larger than our models had room for. The implications for the total galaxy census are still being worked out, but the direction is clear. If the early universe contained far more bright galaxies than predicted, galaxies that were invisible to Hubble and to previous estimates, then every count we made before Webb was missing a significant portion of the early universe's population. The 2 trillion figure from Consellis et al. Already incorporated some extrapolation for faint, unobserved galaxies, but it was built on models that underestimated how many massive, luminous objects existed in the first billion years. Some researchers have tentatively suggested that the true count of galaxies in the observable universe, when Webb's revelations about the early population are fully incorporated into models, may ultimately push the total number significantly higher still, potentially into the trillions upon trillions. The exact figure is genuinely uncertain and actively debated. What is not uncertain is the direction. Every time we have built a more powerful telescope and looked more carefully, the universe has turned out to contain more than we thought. Every single time. Each of those galaxies contains stars, vast numbers of stars. The Milky Way holds somewhere between 200 billion and 400 billion stars. That range alone spans a factor of 2, which tells you something about how hard it is to count even our own galaxy's population. Other galaxies range from a few million stars in dwarf galaxies to several trillion in the largest known elliptical galaxies. If we take a conservative average, perhaps 100 billion stars per galaxy, and multiply by 2 trillion galaxies, we arrive at a number of stars in the observable universe on the order of 200 sextillion. That is a 2 followed by 23 zeros. Around 26,000 times more stars than there are grains of sand on all of Earth's beaches combined, and that is the conservative estimate, built on figures that Webb is now suggesting may still be too low. You are sitting on a planet orbiting one of those stars, inside one of those galaxies. The number of potential worlds implied by that star count is not something human intuition can honestly process. The best we can do is acknowledge the scale and let it change how we understand the word universe. The extraordinary galaxy density of the early universe is not simply a question of counting. What it tells us is that the conditions that allow complexity, that allow stars to form, planets to assemble, chemistry to build toward life, were present in the cosmos far earlier and far more extensively than we had calculated. The early universe was not a barren frontier, waiting for civilization to slowly emerge across billions of years. It was already, within its first billion years, a densely structured environment filled with luminous objects capable of producing heavy elements, building rocky planets and, at least in principle, harboring the conditions for chemistry as sophisticated as our own. The universe had a head start we had not given it credit for, and what that head start means for questions larger than galaxy counts, for questions about what else those early galaxies might have produced, is something no model has yet answered cleanly. More galaxies, more stars, more structure, formed earlier, packed more densely into the first billion years than any simulation predicted. Each individual piece of Webb's data was remarkable, but cosmologists were beginning to notice something about the pattern as a whole. Not just that individual objects were anomalous, but that the large-scale organization of the early universe itself looked different from what the models expected. Not just the contents of the early universe, its architecture. The way those early galaxies were arranged, clustered together, threaded along cosmic filaments, grouped in ways that implied the gravitational scaffolding of large-scale structure had assembled itself far sooner than the timeline allowed. The cosmic web, the vast, interconnected framework of galaxy clusters and dark matter filaments that spans the entire observable universe, was supposed to be a slow product of billions of years of gravitational work. Webb was finding evidence that it had begun taking shape remarkably early, and what that suggested about the timeline of structure formation changed the picture in ways that are still being absorbed. The universe is not scattered randomly. At the largest scales imaginable, it has a shape, a vast three-dimensional web of filaments, nodes, and hollow voids stretching across billions of light years. Scientists call it the cosmic web, and it was supposed to take billions of years to build. Webb found it already taking form when the universe was barely 650 million years old. Gravity is patient. That is the essential claim of cosmological structure formation. The universe begins nearly uniform. Small fluctuations in density are amplified by gravity over billions of years, and slowly, over an almost incomprehensible timescale, the matter of the cosmos organizes itself into the architecture we see today. Galaxy clusters, filaments, vast, empty voids, a skeleton of structure assembled across most of cosmic history. That is the model. Patient gravity, slow construction, billions of years. And then Webb observed galaxy protoclusters, the seeds of massive galaxy. Clusters, already congregating when the universe was 650 million years old. Not slightly ahead of schedule. Not a modest deviation from the predictions. The gravitational architecture of the large-scale universe appears to have begun taking shape at a time when the standard models had not expected it to be anything more than faint, dispersed traces. The cosmic web had not waited for the timetable. To understand why early cosmic structure is so remarkable, we first need to understand what the cosmic web actually is. Look at the universe at the largest scales so vast that individual galaxies become invisible, like individual sand grains invisible from an airplane. And what emerges is a pattern. Galaxies do not spread evenly through space. They collect in long, thread-like filaments that stretch across hundreds of millions of light years, then converge at dense nodes where galaxy clusters gather. Between those filaments, vast hollow voids yawn open, regions almost entirely empty of galaxies, some 300 to 400 million light-years across. The Botha's void, one of the better-known examples, measures roughly 330 million light-years across. That is 3,300 times the diameter of the entire Milky Way, and it contains almost nothing. The filaments, the clusters, the voids, together they form a structure cosmologists call the cosmic web, and roughly 85% of the matter in those filaments is not ordinary matter at all. It is dark matter, an invisible form of matter that neither emits nor absorbs light, detectable only through its gravitational effects. Galaxies do not build the web, they trace it, collecting along the dark matter skeleton like dew along a strand of silk. The cosmic web was built by forces we cannot directly observe, shaped matter into the largest coherent structures in the universe, and only revealed its presence by the visible galaxies that gathered along its edges. The cosmic web assembles through a process called gravitational collapse. In the very early universe, matter was distributed almost, but not perfectly, uniformly. Tiny fluctuations in density existed, regions fractionally denser than their surroundings. Gravity amplified those fluctuations over time. The denser regions pulled more matter inward. Matter drained from less dense regions into them, leaving growing voids behind. Over hundreds of millions to billions of years, the gentle preference of gravity for overdense regions sculpted those initial fluctuations into the filaments and clusters we observe today. The key word in that description is time. The process is gradual. The initial fluctuations were tiny, building a cluster of hundreds of galaxies from those whisper-thin overdensities requires gravity to work continuously, patiently, across a very long baseline of time. The standard simulations, the Millennium Simulation, illustrious TNG, and others, predicted that genuinely rich protoclusters, regions dense enough to eventually collapse into today's most massive galaxy clusters, should be rare or absent at redshifts above 5. At a universe age of roughly 1 billion years or younger, significant clustering should barely be getting started. And then Webb began cataloguing what was actually out there at redshift 7, 8, and beyond. Among the most striking observations from Webb's first years of operation were detections of galaxy overdensities, regions where multiple galaxies are clustered more closely together than the average background density, at redshifts corresponding to 650 million years after the Big Bang. Galaxy overdensities are the direct observational signature of protoclusters. A protocluster is exactly what the name suggests, a region not yet collapsed into a full cluster, but containing the seeds of one, a collection of galaxies bound to each other by gravity, destined over billions of subsequent years to fall together and merge into one of the universe's most massive structures. Webb's infrared sensitivity allowed it to identify protocluster candidates at distances that previous telescopes could not reliably probe, and across multiple survey fields, the JADE survey, the Sears survey, and individual pointed observations, multiple candidate overdensities emerged at epochs when the standard model predicted them to be extraordinarily rare. A protocluster at 650 million years after the Big Bang spans, in physical terms, roughly 3 to 4 million light-years across. To give that a human frame, the distance from our galaxy to our nearest major neighbour, the Andromeda Galaxy, is about 2.5 million light-years. This protocluster stretches across a region roughly 1.5 times that distance, a structure containing multiple massive galaxies already bound together by gravity, already beginning the process of assembly, that will culminate, billions of years from now, in one of the most massive objects in the universe. And it was doing this when the universe was less than 5% of its current age. Here is where the physics becomes genuinely difficult to reconcile. The cosmic web is fundamentally a dark matter structure. Galaxies are passengers. They fall into pre-existing dark matter concentrations. For a protocluster of galaxies to exist at 650 million years, the underlying dark matter, halo, the invisible mass concentration that gravitationally anchors it, must have assembled even earlier. Dark matter, halos of the mass required to host galaxy protoclusters, take time to build up through a process called hierarchical merging. Small halos form first, then merge into larger ones over time. Picture this. Imagine constructing a building not with a crane that places finished floors from the top down, but by allowing small bricks to slowly fall together by gravity, clump into bricks. Those clumps merge into larger ones, and those larger clumps gradually assemble into the structure you see. That is how dark matter halos grow, and the size of halo required to host a galaxy protocluster visible at 650 million years implies that the merger history had already been running at full pace for the entire time available, with almost no margin for delay, no slack in the schedule, and no room for the kinds of inefficiencies that simulations typically predict. How did the gravitational scaffolding assemble itself so efficiently, so early? This is one of the questions Webb's discoveries have placed squarely before the cosmological community, and it does not yet have a clean answer. The tension with simulations is real and documented. Large-scale cosmological simulations, constructed using the best available measurements of dark matter density, dark energy content, and the initial fluctuation spectrum from the cosmic microwave background, do occasionally produce early protoclusters. But the frequency of rich galaxy overdensities at redshifts above 7 in those simulations is significantly lower than what Webb surveys are finding. Two broad interpretations are currently being explored, and neither is settled. The first argues that the simulations are broadly correct, but that Webb is finding the rare tail of an expected distribution, the most extreme overdensities that form earliest, which are predicted but infrequent. On this view, nothing fundamentally new is required. Webb is simply sensitive enough to find the rarities. The second argues that the frequency of early overdensities Webb is finding exceeds what even the rare tail of standard simulations can account for, implying that some aspect of how dark matter assembles at high redshift, or how galaxy formation efficiency varies in dense environments, is not correctly captured in current models. The community is actively debating this. Papers continue to appear on both sides. The honest answer, as of today, is that the jury is still out. But the data Webb is generating has forced a level of scrutiny on large-scale structure formation models that was not present before its first images arrived. What does it mean that the universe's large-scale architecture was assembling itself at 650 million years, rather than waiting for billions of years of patient gravitational work? If protoclusters existed that early, their member galaxies had already been gravitationally influenced by their neighbors for a substantial portion of their entire existence. Dense environments affect how galaxies form stars, how their gas is consumed or stripped, how their black holes grow. The evolutionary history of galaxies inside early clusters is different from that of isolated galaxies. Finding those clusters so early means the environmental shaping of galaxy evolution, the way proximity to other massive objects alters the internal life of a galaxy, was already operating as a factor long before any model had considered it relevant at those epochs. Every galaxy that ever formed inside one of those early protoclusters had its entire history shaped by its neighbors from nearly the beginning. And the material those galaxies produced, the heavy elements forged in their stars, the gas expelled by their black holes, was shared and recycled among those cluster members for billions of subsequent years. Some of that material eventually escaped the cluster, drifted into the broader universe, and became part of the raw material for later generations of stars. Stars, like our own sun, you are, in a way that is not metaphorical but chemically literal, partly assembled from material that passed through environments that looked like those early protoclusters. The earliest large-scale structures the universe built are not remote abstractions. They are part of your own origin story. Galaxies more massive than expected. Black holes too large for their age. A universe more densely populated than any census had counted. And now large-scale structure, the gravitational framework of the entire cosmos, assembling itself faster than the standard model's timeline permitted. Each discovery, taken alone, might be absorbed into the model with careful adjustments. Perhaps star formation efficiency was higher. Perhaps dark matter seeds were more effective. Perhaps the distribution of initial fluctuations was slightly different from assumed. But taken together, these discoveries pointed towards something the cosmological community could no longer ignore. Not a collection of isolated anomalies, but a pattern of systematic tension between what the standard model predicted and what Webb was finding. A tension that had a name in the journals and in the conference rooms, where theorists were now gathering to discuss what it might mean. The model that had survived every test for decades was facing something it had not faced before, not falsification, but genuine accumulating pressure. And the question the community was beginning to ask was not whether individual parameters needed adjusting, but whether something deeper needed to change. Here is something that rarely gets said clearly. Science does not fail when a model breaks. A model that breaks under the weight of new evidence is a model doing exactly what it was built to do. The observations do not defeat the science. The observations are the science. And what Webb is generating right now is something genuinely rare, a stress test that the model may not pass unchanged. For decades, the Lambda CDM model, the standard model of cosmology, passed every test presented to it. Lambda for dark energy, the force driving the universe's accelerating expansion. CDM for cold dark matter, the invisible mass that provides the gravitational scaffolding for everything we can see. Together, they form a framework that explains the cosmic microwave background, the distribution of galaxies across the sky, the abundance of light elements forged in the first few minutes after the Big Bang, and the large-scale structure of the observable universe. Tested against everything we could observe, it held. Not approximately, not within a reasonable margin. It held with extraordinary precision across many independent measurements. Cosmologists could say with genuine confidence that they understood the broad architecture of cosmic history, how it began, how it expanded, how structures formed, how it would end. The Lambda CDM model was one of the most successful predictive frameworks in the history of science. And then, one telescope pointed at the early universe, and the data that came back did not match. Every model is only as credible as its predictions, and Lambda CDM had made very specific predictions about what the early universe should look like. Galaxies in the first billion years should be small. They had not had time to grow large. The process of galaxy formation anchored to the gradual growth of dark matter, halos through hierarchical merging, smaller concentrations slowly assembling into larger ones, is a time-consuming process. The model predicted that the earliest galaxies would be faint, irregular, chemically primitive structures containing relatively modest amounts of stellar mass, forming stars at moderate rates. Some would be bright, but the brightest, most massive examples should be vanishingly rare at high redshift. Star formation efficiency, the fraction of a galaxy's available gas that actually converts into stars, was predicted to be low. The universe is not an efficient star factory. In our own Milky Way, only about 2 to 4% of the available gas converts to stars at any given time. The rest is heated, expelled, or simply never collapses under the right conditions. 3% efficiency. That is the rough baseline built into the models for galaxies across cosmic time, and the models worked. Applied to the universe we could observe, those predictions matched what Hubble found at moderate distances, what ground-based surveys catalogued, what simulations replicated. 3% efficiency was not a guess, it was a measured, empirically grounded input. That was the belief, well-founded, long confirmed, settled. Then Webb arrived with its infrared eyes, its extraordinary sensitivity, and its ability to peer back to redshifts above 10, to a universe younger than 5% of its current age. And the galaxies it found were too bright, too massive, too numerous, and too structured. Each anomaly, reported separately in the first papers emerging from Webb surveys, might have been dismissed. Photometric redshift errors, gravitational lensing amplification, unusual individual objects at the tail of the expected distribution. Scientists are trained to be cautious, and the early response across the community was exactly that: measured, skeptical, demanding confirmation. But the confirmations came. Spectroscopic follow-up solidified the distances. Mass estimates were carefully revised, scrutinized, and revised again, and paper after paper arrived at the same uncomfortable conclusion. The early universe, as Webb sees it, contains more structure and more stellar mass than the standard model's star formation efficiency allows. In 2023, Michael Boylan Colchin, an astrophysicist at the University of Texas at Austin, published an analysis in Nature Astronomy that framed the problem with unusual precision. He calculated what would happen if you assumed the most massive early galaxy candidates Webb had identified were real, and then asked whether the available baryons could account for their stellar mass. Baryons are ordinary matter, the protons and neutrons that make up every star, planet, and person. A dark matter halo of a given mass contains a calculable amount of baryonic matter, and that amount sets a hard ceiling on how much stellar mass a galaxy inside that halo can possibly contain. When he ran the numbers, some of the most extreme early galaxy candidates required converting nearly all of their available baryonic matter into stars. Not 20%, not 50%. For the most extreme cases, approaching the absolute physical ceiling, a star formation efficiency of close to 100%, in a universe where 3% was the measured norm. Scientists do not sit comfortably with a broken model. The question was not whether to investigate, but where to begin. Several genuine, distinct explanations entered the debate almost simultaneously, and they remain actively contested today. The first explanation involves black holes. Some researchers, drawing on NASA-supported analysis, proposed that at least some of the early galaxies Webb identified as extraordinarily luminous were not producing all of that light through stars alone. An active galactic nucleus, a supermassive black hole at the center of a galaxy that is actively consuming surrounding matter and radiating enormous energy, can outshine an entire galaxy of hundreds of billions of stars. If early galaxies contained active black holes whose light was being incorrectly attributed entirely to stellar mass, then the true stellar populations would be smaller. The apparent tension with lambda CDM would shrink, and no fundamental revision to the model would be required. Imagine a bonfire at the center of a stadium. Photograph the stadium from space and attribute all the light to seats. You would dramatically overestimate the number of seats. That, in essence, is the concern about AGN contamination, using a galaxy's total luminosity as a proxy for stellar mass, when some of that luminosity comes from its central black hole. The second explanation involves what cosmologists call bursty star formation. Rather than forming stars at a steady rate, some early galaxies may form them in intense, brief episodes, burning brilliantly for tens of millions of years, then quieting dramatically. Webb surveys that catch galaxies during their luminous bursts would overrepresent the bright phase and create a false impression that the early universe was systematically populated with extremely massive, continuously luminous objects. On this view, the apparent excess is a sampling bias, not a physical anomaly. The third explanation is more structurally significant. Perhaps the conditions in the early universe genuinely allowed for higher star formation efficiency. The early universe was denser, hotter, and richer in the kinds of cold gas clouds that most efficiently collapse into stars. If the physical environment was simply different enough that 20 or 30% of available gas converted to stars rather than 3%, the model's parameters would need revising, but its fundamental architecture would survive. And the fourth explanation is the one scientists are most reluctant to reach for, but the one they cannot rule out. Something in the underlying physics, in how dark matter behaves, in how the initial fluctuation spectrum is characterized, or in the nature of dark energy itself, may need revision, not simply a parameter adjustment, a structural change. Here is the honest picture as of today. No single explanation has won. No consensus has formed. The community is in the middle of an active, good faith empirical investigation, running more spectroscopic observations, building more detailed simulations, refining mass estimates, and scrutinizing every assumption that went into both the observations and the models. Picture this. A meticulous engineer discovers that a bridge she has designed is behaving slightly differently from the calculations under certain load conditions. She does not immediately conclude the underlying physics of materials is wrong. She checks her measurements. She reviews her assumptions. She considers whether the conditions were as she modeled them. Only after exhausting every instrumental and methodological explanation does she consider whether the model itself needs to change. That is exactly the process cosmology is now, running carefully, rigorously, without premature conclusions in either direction. What is clear is the direction of the evidence. Every Webb survey that returns data adds to a picture that is systematically inconsistent with what the standard model predicted for the early universe, not uniformly, not catastrophically, but persistently and across multiple independent lines of observation. The history of cosmology is, in one reading, a history of models that broke and were replaced by something richer. Einstein's general relativity predicted a static universe. When Edwin Hubble's observations revealed that the universe was expanding, Einstein called his static universe assumption the greatest blunder of his career. The model did not collapse, it grew. The field equations that had predicted a static cosmos also predicted an expanding one, and the expansion Hubble found fit them perfectly. The theory survived by absorbing an observational blow that should have undone it. Later, the steady-state model, which held that the universe had no beginning and had always existed in essentially its current form, seemed reasonable and was defended with genuine conviction. The discovery of the cosmic microwave background in 1965, the faint afterglow of the Big Bang itself, ruled it out almost overnight. Not because scientists wanted it to fail, because the data was unambiguous. Lambda CDM emerged from that history as the most successful successor, absorbing every available observation and still fitting. The question Webb is now forcing is whether it will absorb these two with parameter revisions or whether something deeper needs to change. The scientific community does not know the answer yet. That is not a failure. That is exactly where the frontier of knowledge is supposed to live. You are watching, from your position in the year 2026, the early stages of what may prove to be one of the most significant revisions in the history of cosmology, or a refinement of existing parameters that leaves the model essentially intact. That question is genuinely open. Observational data continues to arrive from Webb. Spectroscopic surveys are ongoing. Theoretical papers are being published at a rate that the journals are working to keep pace with. What is not uncertain is that the process unfolding, the careful collection of data, the honest confrontation between observation and prediction, the willingness to question a model that has been among the most successful in scientific history, represents science functioning at its best, not broken, not in crisis, alive, actively learning, and capable of being surprised by the universe it is trying to understand. Every great scientific revision in history has looked from the inside like a stress test, a moment when the data will not fit, the explanations keep multiplying, and no one is quite sure what the new picture will look like when it finally comes into focus. We are inside one of those moments right now. The debate over what Lambda CDM can absorb and what it cannot will take years to resolve. More Webb data, more spectroscopic confirmation, more theoretical modeling. The frontier is genuinely open, and the outcome is genuinely uncertain. But while that debate was unfolding among theorists and observational astronomers, a quieter and equally profound reassessment was happening in parallel. Because the anomalies Webb found in the early universe did not just challenge our models of how galaxies form, they challenged our accounting of how many galaxies exist, and of how many stars, and of how many worlds. The original census, already expanded from 200 billion to 2 trillion galaxies, was being looked at again in light of everything Webb had revealed about how much the early universe had been undercounted. And the numbers that were beginning to emerge from that reassessment were staggering in a way that carried implications far beyond cosmology. The universe, it was becoming clear, was not merely larger than we had measured, it was larger than we had been able to imagine measuring. The number 200 billion was wrong. 2 trillion may also be wrong. Every time we have built a more powerful instrument and turned it toward the sky, the census has grown. And what Webb is now revealing about the early universe suggests that the most fundamental count we have, how many galaxies exist, may need to be revised upward again. Not by a small amount. Astronomers do not revise galaxy counts casually. The 2 trillion figure, arrived at in 2016 by Christopher Consolis's team at the University of Nottingham, published in the Astrophysical Journal, was a careful, rigorous piece of work. It used Hubble's deepest observations, modelled the distribution of galaxies too faint for any telescope to directly detect, and concluded that the observable universe likely contains not the 200 billion Hubble had originally suggested, but 10 times that number. That revision alone, from 200 billion to 2 trillion, was staggering. 2 trillion galaxies, each containing hundreds of billions of stars, filling every direction of the sky so completely that if you could see them all simultaneously, the darkness between them would nearly disappear. But that estimate was built on models that assumed the early universe looked the way the standard simulations said it should. Webb has now shown, survey after survey, that those simulations underestimated the early universe's population of bright, massive galaxies. Which means the Constellus estimate, extraordinary as it already was, may have been counting against a baseline that was itself too low. The number is being revised. Again. To understand what Webb's data changes, it helps to understand how we arrived at 2 trillion in the first place. Hubble could see galaxies directly, down to a certain brightness threshold, and count them in small patches of sky, then extrapolate across the whole sky. That method produced the original 200 billion. But Constellus's team realized that this direct counting method was missing a population of galaxies that existed in great numbers in the early universe, but were simply too faint and too small for Hubble to detect individually. Their models predicted that population should be enormous, and when they added the extrapolated count to the directly observed count, the total rose to 2 trillion. The critical point is that those extrapolations were based on simulations built on lambda CDM, simulations that, as we now know, underestimated the brightness and mass of early galaxies. If the real early universe contained more luminous, more massive galaxies than the models predicted, which is precisely what Webb's surveys are finding, then the Constellus estimate may have used a baseline that was too conservative. The direction is clear, the exact revised number is not yet settled. Scientists are actively working on new estimates that incorporate Webb's observations into the population models. What they are working toward is not a modest adjustment. Every indication from Webb's data points toward a universe that is, by any measure of population, more richly populated than we had calculated. Every upward revision of the galaxy count carries a proportional implication for the total number of stars in the observable universe. The current conservative estimate, derived from the 2 trillion galaxy figure and an average of roughly 100 billion stars per galaxy, places the total stellar population of the observable universe at around 200 sextillion stars. That is, A2 followed by 23 zeros, 100 billion times 2 trillion. The number is so large that no analogy makes it feel genuinely small, but consider the most generous estimates of the total number of grains of sand on all of Earth's beaches, every coastline, every desert shoreline, every river delta and sandbar on the planet, come to roughly 7.5 quintillion. That is a 7 followed by 18 zeros. The star count exceeds the beach sand count by a factor of roughly 26,000. Stars outnumber the grains of sand on every beach on Earth by an enormous margin, and that is before Webb's corrections to the galaxy census are applied. If the galaxy count rises, as Webb's data strongly suggests it should, the star count rises with it, and with every additional star comes the statistical implication of additional planetary systems. The Kepler Space Telescope, which spent years surveying a portion of our own galaxy, found that roughly 1 in 5 Sun-like stars host a rocky planet in the habitable zone, the region of space around a star where liquid water could exist on a planetary surface. That is the condition considered most relevant to the kind of chemistry that, on at least one planet we know well, produced biology. 1 in 5. That sounds modest. Applied to 200 sextillion stars, it yields a number of potential habitable zone rocky worlds in the observable universe of approximately 40 sextillion. That is 40 followed by 21 zeros. 40 sextillion potential worlds where, in principle, liquid water could pool on a surface under a warming sun. And that is the conservative count. Before Webb's revisions, the number of potentially habitable worlds in the observable universe alone almost certainly exceeds anything the human mind can honestly process. And what makes this particular number different from purely abstract enormity is its implication. The conditions that produced you, a rocky planet, a moderate star, liquid water, a geologically active surface, an atmosphere are not exceptional. They are, by any reasonable statistical reading, extraordinarily common. What if you could stand at the edge of the observable universe, not approaching it, not watching it from here, but actually positioned at the outermost boundary of what our instruments can reach? From that vantage point, you would look in one direction and see the entire 13.5 billion years of observable cosmic history arrayed before you. In the foreground, nearby galaxies, spirals and ellipticals like the ones in our local group. Further back, galaxies growing smaller, more numerous, redder. Deeper still, the faint, compact structures of the early universe, the ones Webb has been cataloguing, dense, luminous, more numerous than anyone expected. And at the very limit of your view, the faint wash of the cosmic microwave background, the afterglow of the Big Bang itself, the moment the universe first became transparent to light. And then you would turn around. In every direction beyond that boundary, space continues. The universe does not stop where our instruments stop. The boundary of the observable universe is not a wall or an edge. It is simply the limit of what light has had time to reach us from since the Big Bang. Space extends beyond it in every direction, carrying galaxies, stars, and worlds that no observer anywhere in the observable universe will ever be able to detect. Not with any telescope we could ever build. Not in any amount of time the universe has left to offer. The observable universe, all 93 billion light-years of it, with its trillions of galaxies and its sextillions of stars, is almost certainly a small, bounded window into a cosmos that continues, unobserved and unobservable, for distances our mathematics can gesture toward, but our instruments will never reach. This question has a genuinely honest answer. We do not know, but we can reason about it carefully. The theory of cosmic inflation, the extraordinarily rapid expansion the universe underwent in the first tiny fraction of a second after the Big Bang, predicts that the universe expanded to a size vastly larger than the region that would eventually become our observable universe. The mathematics of inflation suggests that the total universe is, at the most conservative lower bound, something like 10 to the power of 23 times larger in volume than the observable universe. That is 100 sextillion times more volume, containing, if the universe is roughly uniform, roughly 100 sextillion times more galaxies, stars, and potentially habitable worlds than we can observe. Imagine this. Suppose the observable universe were the size of a single room in a building. The total universe, on these estimates, would be a building so enormous that standing in your one room and looking out through its one window, you would have no means, none, of determining the building's size. You would know the room. You would know nothing beyond the walls you can reach. That is our situation. The 93 billion light-year observable universe is our room. It is everything light has had time to bring us, and beyond its boundary, space continues in a silence we cannot break, and a darkness our light will never illuminate. When we say the universe is larger than we thought, more galaxies, more stars, more worlds, we are not simply adding to a ledger of impressive numbers. We are revising our understanding of the context in which we exist. Everything that has ever happened on this planet, every species that has evolved, every civilization that has risen and fallen, every thought that has been thought, every discovery that has been made, has happened on a single rocky world, orbiting a single ordinary star, inside a single ordinary galaxy, inside an observable universe that is itself almost certainly a vanishingly small fraction of the full extent of space. That is not a diminishment. That is a clarification. The universe does not become less meaningful because it is larger than we thought. The fact that the conditions for chemistry, for biology, for minds capable of wondering about their place in the cosmos, appear to be extraordinarily common across a cosmos of almost incomprehensible scale, that fact does not reduce you, it locates you. Precisely, honestly, and in a way that no previous generation of human beings has had the instruments to understand. You are here, and the universe in which you are here is richer, more structured, and more teeming with potential than anyone who came before us had any way of knowing. All of this, the revised galaxy counts, the star populations, the sextillions of potentially habitable worlds, the observable universe as a single room in a building whose size we cannot know, raises a question that goes further than astronomy, deeper than cosmology. If the conditions that produced life on Earth are so common, if the early universe was forming galaxies and building complex chemistry far earlier than we predicted, if the total number of potentially habitable worlds is not in the billions or the trillions, but in the sextillions and beyond, then the question of what else might have emerged from all of that time, all of that chemistry, all of those worlds is no longer a question about remote possibility. And that question leads somewhere unexpected, somewhere that changes not just how we understand the universe, but how we understand our place within the window of time we have been given to observe it. A universe that formed its first galaxies 320 million years after the Big Bang. Stars that lived and died and scattered heavy elements before our sun existed. Planets that could have assembled from that material billions of years before Earth was born. This is not speculation. The arithmetic follows directly from what Webb has confirmed, and where it leads is extraordinary. Every discovery Webb has given us, the early galaxies, the oversized black holes, the proto-clusters assembling when the universe was less than 5% of its current age. Each of these findings, taken alone, is a revelation about cosmology, about structure formation, about the limits of our models, but follow the implications far enough and they reach something more intimate than cosmology, something that, if you sit with it long enough, changes the way you think about what this universe is and what it might contain. The universe formed its first massive galaxies within the first few 100 million years. Those galaxies contained stars. The most massive of those stars burned briefly and brilliantly, a few million years each, and when they died, they scattered the heavy elements needed to build rocky planets: carbon, oxygen, silicon, iron. The raw materials for planets like Earth were present in the universe remarkably early, and rocky planets do not take long to form once the raw materials are available, perhaps 100 million years under the right conditions. Walk through that arithmetic slowly. The first heavy elements forged in stellar furnaces, the scattered material drifting into new clouds, new stars forming, planets assembling around them. All of this potentially within the first 500 million years after the Big Bang. Earth formed 9.2 billion years after the Big Bang, which means if the timeline above is roughly correct, and Webb's observations make it at least plausible, rocky worlds could have been forming nearly 9 billion years before Earth existed. 9 billion years is not a number that carries meaning when stated plainly. So, consider it differently. The oldest confirmed evidence of life on Earth, microbial traces in ancient rock formations in Western Australia, dates to roughly 3.5 billion years ago. 3.5 billion years of biological history on this planet, from the first single-celled organisms through every species that has ever lived, every ecosystem that has ever assembled, every evolutionary innovation from photosynthesis to the vertebrate eye to the human brain. All of it unfolded across 3.5 billion years. The head start that early rocky worlds may have over Earth is more than twice that entire span. 9 billion years, 2.5 times the entire history of life on Earth. All that time available on worlds that formed from the first generation of heavy elements scattered by the first generation of dying stars. What could that time produce? The question is genuinely unanswerable, but it is no longer idle speculation, because Webb has shifted the terms of the question. Where it once seemed reasonable to ask whether the conditions for planets and life existed early in cosmic history, the data now makes it difficult to argue they did not. The materials were there, the energy sources were there, the timescales were available, and the number of worlds on which those conditions could have played out is, as we have established, measured in the sextillions. In the summer of 1950, the physicist Enrico Fermi was eating lunch with colleagues at the Los Alamos National Laboratory in New Mexico when the conversation turned to the question of extraterrestrial intelligence. At some point, Fermi, one of the architects of the atomic age, a man whose instinct for the essential question was legendary, paused and asked something simple. Where is everybody? That question has carried his name ever since. The Fermi paradox. Not a paradox in the strict logical sense, but a profound dissonance between what the scale and age of the universe seem to imply and what we have actually observed. The reasoning behind the paradox is stark. The Milky Way alone contains hundreds of billions of stars. Many of those stars host planets. Among those planets, many likely orbit in the habitable zone where liquid water could exist on the surface. Some fraction of those planets presumably developed life. A smaller fraction may have developed complex life. A smaller fraction still may have produced technological civilizations capable of communication or travel. And the Milky Way is 10 billion years old, more than enough time, given our own example, for a technological species to emerge, develop spacefaring capability, and potentially make its presence detectable across interstellar distances. The Milky Way should, by this reasoning, be teeming with evidence of intelligence, signals, structures, something, and we have found nothing. Here is where Webb's discoveries sharpen rather than resolve the question. Before Webb, the Fermi paradox rested on an uncertain foundation. We were not sure how early or how commonly the conditions for planet formation had existed. A skeptic could always argue that complex life requires extraordinary conditions, a very particular kind of star, a very particular arrangement of neighbouring planets, a very particular chemical composition, and that such conditions had only recently become widespread enough to matter. The universe might be vast, but perhaps it was also young in the ways that counted. Webb has closed some of that escape route. The building blocks of rocky planets were present within the first half-billion years. The universe has had nearly 14 billion years to run the experiment of life on an enormous number of potentially suitable worlds. And as we have seen, those worlds number not in the billions but in the sextillions, even within the observable universe alone. The Fermi paradox is, if anything, more pointed after Webb than it was before. More galaxies, earlier planet formation, more time than anyone had calculated, and still, across 70 years of radio telescope surveys that have listened carefully to hundreds of thousands of stellar systems, not one confirmed signal of intelligence beyond Earth. Scientists have proposed many explanations, and none has been ruled out. Perhaps the emergence of complex life requires a rare sequence of biological luck that occurred on Earth, but has not occurred elsewhere. Perhaps technological civilizations reliably destroy themselves before they can communicate across interstellar distances. Perhaps the universe is genuinely young in the ways that matter, and we may be among its first technological species, not one of countless many. Perhaps intelligence has arisen elsewhere, but communicates through methods we have not yet conceived of, making our radio frequency searches the cosmic equivalent of looking for smoke signals from people who use the internet. No one knows. The honest scientific position is that the Fermi paradox remains completely unresolved. But here is what Webb has done to it. It has made the question impossible to dismiss. Imagine standing on the surface of a rocky world orbiting a second-generation star, a star that formed from the scattered remains of the first generation that lived and died in the early universe. The date, in cosmic terms, is approximately 500 million years after the Big Bang. That is 8.7 billion years before Earth will form. The sky above you is darker than Earth's sky at noon, but the stars are more numerous and more densely packed than anything visible from our planet. The universe is younger and smaller. not yet expanded to its current vastness, and the night sky blazes with the light of a cosmos, still dense with recently formed stellar nurseries. In the distance, the faint smear of neighbouring galaxies hangs low enough to cast shadows. The atmosphere around you is different from Earth's. The chemistry is different. The geological processes reshaping the surface beneath you are different. But the physics is the same. The same forces that guided matter into stars on Earth guided it here. The same chemistry that allowed amino acids to form in our early ocean allows it here. The same energy from this star falls on this surface and drives the same thermodynamic gradients that on Earth drove the first biochemistry. Whether life of any kind emerged on a world like this, whether the 9 billion years between its formation and ours produced anything recognizable, is a question we cannot answer today. But standing there, looking up at a sky burning with early stars, the question does not feel remote or abstract. It feels urgent and human. There is one more piece of this picture that changes the context profoundly. The stars most likely to host habitable worlds for the longest periods are not stars like our Sun. Our Sun is a yellow dwarf star, medium-sized, moderate temperature, and will remain stable for about 5 billion more years before expanding to engulf the inner planets. That gives Earth's biosphere roughly 5 billion additional years before the Sun makes the surface uninhabitable. A generous window, but a finite one. Red dwarf stars, the smallest, coolest, most common stars in the galaxy, burn so slowly and so gently that their lifespans are not measured in billions of years but in trillions. A red dwarf star like the ones that make up roughly 75% of all stars in the Milky Way will remain stable and habitable zone producing for up to 10 trillion years. That is 10 trillion. Written out, a 1 followed by 13 zeros. Our universe is currently 13.8 billion years old. 13.8 followed by 9 zeros. The fraction of the red dwarf. Habitable era that has so far elapsed is less than 1/10 of 1%. If you want a comparison, imagine the entire future habitable era of the universe as a single year. We are currently about 12 hours into January 1st. The universe is not in its final chapters. By the measure of the stars most suited to harbouring life for the longest time, the universe has barely begun. The vast majority of the worlds that will ever be warm, lit by patient stars, with liquid water on their surfaces, and the possibility of chemistry building toward complexity, those worlds have not yet formed. The cosmic history of life, if it exists beyond Earth at all, is almost certainly still in its prologue, which means that whatever life has arisen in the 9 billion years before us is history, and whatever emerges in the 10 trillion years ahead is a future so vast that every analogy we have exhausted in this journey so far would fail to contain it. We have travelled a long way together, from the first galaxies that should not have existed, to black holes that grew too fast, to a cosmic web assembled ahead of schedule, to a universe more populated than any census had counted. From the first surprise to the last revelation, from the limits of what Hubble could see to the edges of what any instrument ever built has observed. Somewhere along the way, perhaps at the first image from Webb, perhaps at the moment we walk through the arithmetic of 2 trillion galaxies, perhaps somewhere quieter than that, this stopped being just a story about a telescope. The universe is not the place we thought it was when this began, and neither, perhaps, are we. Every discovery Webb has returned, the anomalies, the excess, the structures that formed too early, the populations that were larger than predicted, each one has been a single thread. Followed carefully, each thread led somewhere deeper than the one before it, deeper into the early universe, deeper into the limits of our models, deeper into the question of what a universe this large, this old, and this richly structured actually is. And now all those threads are in our hands at once, not as separate findings from a remarkable telescope, but as a single, coherent portrait, a portrait of a universe that has consistently exceeded every estimate we have made of it, every count, every timeline, every prediction of what we would find when we looked carefully enough. The true scale of the universe has never been purely a matter of distance, not just how wide it is, or how many galaxies fill it, or how long it has existed. The true scale is what all of that implies about the nature of what we are part of, about what this cosmos is, and what it contains, and what it means that out of all of it, all its trillions of years and sextillions of worlds, something small and brief and improbable assembled itself on one of those worlds, built a machine, pointed it at the sky, and began to understand. That is where we are going, and that is what we have been building towards since the first photon arrived. Every discovery Webb has returned has been, in some sense, the same discovery. The universe was more than we thought, more structured, more populated, more active, more ancient, more capable. The measurement kept changing, the direction never did, and now, having followed every thread to where it leads, we can finally ask the question this entire journey was building toward. By the summer of 2022, the scientific community had reason for something close to confidence. The James Webb Space Telescope had launched without incident, deployed without failure, aligned its 18 golden mirror segments, cooled its instruments to within 7 degrees of absolute zero, and begun returning images of unprecedented clarity and depth. The first full-color images arrived on July the 12th, 2022, and they were by any measure staggering. Scientists knew what they would find, broadly speaking. They expected Webb to confirm and refine the picture that Hubble had built. Over 30 years. Earlier galaxies, yes. Fainter objects, certainly. Perhaps some surprises at the margins. But the architecture of the story, the Lambda CDM model, the timeline of structure formation, the galaxy populations at various epochs, all of that was expected to stand, sharpened by Webb's superior sensitivity, but fundamentally confirmed. For a brief moment, as the first images circulated through the community, that seemed to be exactly what was happening. And then the data began to arrive in volume, survey after survey, galaxy after galaxy, at redshifts that should have been impossible, black holes that should not yet exist, protoclusters assembled ahead of schedule, populations of early galaxies that exceeded every simulation's prediction. Webb did not confirm the picture. Webb replaced it. Not with chaos, not with contradiction, with something richer, deeper, and more extraordinary than the picture it superseded. A universe more actively structured, more densely populated, more chemically advanced in its earliest chapters than any model had anticipated. A universe that had been building complexity since nearly the beginning, and had been doing so on a scale our instruments had simply not been able to see. Let us place all of it in one frame. The universe began 13.8 billion years ago in a state of extraordinary uniformity, hot, dense, and almost perfectly smooth. By the time it was 320 million years old, a galaxy was already forming that Webb has since observed and confirmed. Compact, luminous, containing a stellar population that required extraordinary conditions to assemble so quickly. By 650 million years, protoclusters were taking shape, the seeds of the large-scale cosmic architecture we trace today. By 700 million years, galaxies with stellar masses comparable to the Milky Way already existed. Objects that should have required billions of years to assemble, somehow completed in a fraction of that time. Ancient black holes had grown to masses that the standard model's mathematics could barely accommodate. The cosmic web had begun its assembly far earlier than predicted, and the total population of galaxies, stars, and worlds was not merely larger than Hubble had shown, it was larger than Hubble's models had the room to contain. The observable universe spans 93 billion light-years from one horizon to the other. 93 billion light-years, a distance so large that if you could travel at the speed of light, the fastest speed physics permits, covering 300,000 kilometers per second, or roughly 186,000 miles per second, it would take 93 billion years to cross it, more than 6 times the current age of the universe, and that entire span, in every direction, is filled with structure that has been building since the universe was barely a few hundred million years old. Filaments and voids, clusters and protoclusters, trillions of galaxies, each containing hundreds of billions of stars, each star a fusion furnace that spent its lifetime converting hydrogen into heavier elements and scattering them into space. This is the universe Webb has revealed, not a cosmos that slowly assembled itself over patient billions of years from a sparse and primitive beginning, a cosmos that hit the ground running, structured, active, and extraordinarily productive from very nearly the start. And yet, what Webb has revealed is not a completed picture. Every answer it has returned has been accompanied by questions deeper and more demanding than the ones that preceded it. The tension between the standard model and the early galaxy population remains genuinely unresolved. The mechanisms that allowed galaxies to assemble so quickly, stars to form so efficiently, black holes to grow so fast, these are actively debated and not yet understood. The total population of galaxies in the observable universe is still being revised. The nature of the dark matter that provides the gravitational scaffolding for all visible structure remains one of the deepest unsolved problems in physics, and the universe that extends beyond our observable horizon, the region from which no light has yet had time to reach us, remains as invisible and unknowable as it has ever been. The true scale of the universe includes its unknowns. A measurement that stops at the edge of what we can observe is not a complete measurement. It is a window, and Webb has shown us that the window is smaller relative to what lies beyond it than we had calculated. Picture this. You are standing in a house at night, looking out through one window at the street outside. The window shows you something real: the street, the lamppost, the trees beyond. But the house does not end at the window frame. The street does not end where the light falls. The world continues in every direction that the window cannot show you. That is our position. Webb has cleaned the glass of our one window and sharpened the view dramatically. What we see now is clearer and richer than anything we have seen before, but the window itself, the observable universe, bounded by the distance light has had time to travel since the Big Bang, remains exactly the same size it was before the first image arrived. What lies beyond it, carrying in silence through unobservable space, continues regardless. Every model that came before Lambda CDM was replaced not because scientists failed, but because they succeeded. Newton's laws described a universe with extraordinary accuracy, and then, when measurements became precise enough to detect their limits, general relativity absorbed what Newton had built and extended it further. The static universe fell to Hubble's data. The steady-state model fell to the cosmic microwave background. Each replacement was not a retreat, but an advance, a demonstration that the universe is always more complex than the model currently describing it, and that the discipline of measurement would eventually reveal that additional complexity. Lambda CDM has survived every test presented to it across the last 3 decades. Webb is presenting new tests, and the results of those tests are generating genuine pressure on specific aspects of the model, particularly its predictions for the early galaxy population, the timeline of large-scale structure formation, and the star formation efficiencies in the first billion years. Whether that pressure produces a parameter revision or something structurally deeper, the scientific community does not yet know. The measurements continue. The papers continue to arrive. And that process, the honest, unglamorous, generation-spanning process of observing, revising, and observing again, is itself a remarkable thing. In 3 years of operation, a single telescope has generated enough data to keep thousands of researchers occupied for decades. The early universe that Webb is revealing is not a finished portrait. It is the beginning of a portrait that no single generation of scientists will complete. That, too, is part of the true scale. When this journey began, we said something simple about telescopes, that they are, in a sense, time machines, that the light reaching any telescope has been travelling since it left its source, and the further the source, the older the light, that every photon is an ancient message, that when Webb detects light from a galaxy that existed 320 million years after the Big Bang, that light has been travelling toward us for 13.48 billion years, longer than Earth has existed, longer than our sun has burned. A message dispatched from the early universe, crossing the entire span of cosmic history, arriving at a golden mirror in the dark of space in the year 2022. That was the image we started with. Old light, travelling toward us, messages from the beginning, arriving now. But after everything we have learned, that image is no longer complete, because the light is not the only thing that made that journey. The atoms in your body, the carbon in your cells, the calcium in your bones, the iron in your blood, were forged inside stars, massive stars that formed, burned, and died in the first generations of galaxies the universe produced. Galaxies like the ones Webb has now observed, stars that lived their brief, brilliant lives in the first few 100 million years of cosmic history, scattered their contents into space when they died, and watched, in the only way a dead star can watch, which is not at all, as that scattered material drifted across millions of years into new clouds, new stars, new planetary systems. Some of that material, across a chain of stellar generations spanning billions of years, became the molecular cloud that collapsed into our sun. Some of it became Earth. Some of it, through processes of chemistry and biology that took another 4 billion years to unfold, became the atoms that are now arranged, briefly and improbably, into you. The light from those early galaxies has been travelling toward us for 13.5 billion years. And so, in a different and equally real sense have you. You are assembled from the same ancient material as the light. Both of you, the photons and the person receiving them, are the universe's oldest material, still in motion, still arriving. We looked at the sky and called it observation, but the sky has always been looking back, not as an act of consciousness, but as the simple fact that the atoms we are made of and the light we detect were born in the same fires, in the same ancient chapter, in the same cosmos that we are only now beginning to honestly measure. The true scale of the universe is not a number, not 93 billion light years, not 2 trillion galaxies, not a septillion stars, or a sextillion potentially habitable worlds. The true scale is what those numbers imply about the depth of time and the extent of matter and the patience of light, and about the fact that somewhere inside all of it, something assembled itself that is capable of holding those numbers, weighing them, and finding them extraordinary. The universe does not know it is large. The galaxies do not know they formed too early. The ancient black holes do not know they grew too fast. The cosmic web does not know it assembled ahead of schedule. None of it knows anything. The knowing, the measuring, the revising, the wondering, that is entirely ours. A brief, local, improbable capacity that emerged on one world around one ordinary star after 13.8 billion years of the universe, doing what the universe does in complete indifference to being observed. And yet we are here, observing, revising, building better instruments, pointing them at the earliest light, and finding more than we expected every time without exception. That is the true scale of the universe, not what it contains, what it produced, and what that production, in this one unlikely corner, learned to notice about the rest of it. The light is still travelling, all of it, From every galaxy Webb has seen and every galaxy beyond the range of any instrument we will ever build, crossing distances that dwarf every comparison we have tried to construct, arriving or not arriving, absorbed or scattered or still in transit across a cosmos that has been expanding for nearly 14 billion years and shows no intention of stopping. Some of that light will never reach us. Some of it arrived this morning, absorbed by Webb's mirror, converted to data, processed by instruments built and calibrated by human hands, and is now being studied by human minds that will spend their careers trying to understand what it means. We are not observers standing outside the universe, measuring it from a safe distance. We are the universe, briefly assembled into something that can measure itself, made from its oldest material, lit by its ancient fires, still and always in the middle of the journey. And now, after all of that, after the trillions of galaxies and the ancient black holes and the light that has been traveling since before the Earth existed, we come back to this room, this night, this quiet. The observable universe spans 93 billion light years in every direction. Trillions of galaxies fill it. Sextillions of stars burn inside them. And somewhere at the edge of what any instrument will ever see, light from the universe's first chapter is still arriving, still crossing distances that make every comparison we have tried to build feel small. And you are here, not at the center of any of it, not in a special position, not on a remarkable world by the universe's indifferent measure. Just here, in a room, on a planet orbiting one ordinary star among hundreds of billions, inside one ordinary galaxy among trillions. But here is the thing about ordinary. The universe built all of that, every filament, every cluster, every ancient galaxy Webb has ever photographed. And out of all of it, in all that immensity, produced exactly this, something small enough to sit quietly in the dark and find it beautiful. That is not nothing. That is everything.